In the last section, we looked at sequences, both those given by a simple defining formula and those defined recursively by a difference equation. In this section, we'll investigate what happens to the terms of a sequence in the long run. In other words, we explore what happens to a sub n as n becomes large. We'll start by introducing the notation and the definition for a limit of a sequence. So in general, we write limit of a sub n as n goes to infinity equals L if the terms for the sequence a sub n approach L as n becomes large. Right? So as we move on into our sequence and keep looking at terms that are farther and farther in the sequence, our sequence is getting close to a value L. And what we mean by close to a value L, the definition says that we can get our terms to be as close to L as we would like by taking an n value that's sufficiently large. So we go far enough into our sequence, we can get as close to the value L as we would like, right? And if that limit exists, if we can do that, we say our sequence converges. And if we cannot do that, we cannot get arbitrarily close to a value L, we say the sequence diverges. And if a sub n becomes large, we say that limit as n goes to infinity of a sub n is infinite. And we say a sub n diverges to infinity. The sequence diverges to infinity. Okay, so let's look at some examples. So in our first example, we want to know what happens to the terms of the sequence a sub n equals -1 to the n minus 1 over n plus 4 as n becomes large. In the last video, we had actually examined this sequence and we found the first 5 terms to be 1/5, -1/6, 1/7, -1/8, 1/9. So we can see in this sequence as the denominator gets bigger, the fraction as a whole keeps getting smaller. The absolute value of these terms are going to get closer and closer to 0, and then the negative isn't going to make a difference. So if I look at the graph of the first 30 terms of this sequence, we'll see that the sequence alternates back and forth above and below the x-axis, but it keeps getting closer and closer and closer. And as we go far enough into this sequence, we can get as close to 0 as we would like. So we say that the limit of this sequence is 0. Here's another example. We want to know what happens to the terms of this sequence n over n plus 1 as n becomes large. So once again, if we write a few of the terms, so the first term is n is 1, I have 1 over 1 plus 1, which is 1 over 2. The second term would be 2 over 3. The term after that would be 3 over 4, and so on. And we can look at the decimal values of these fractions. 1/2 is 0.5, 2/3 is 0.6 bar, so it's getting larger. 3/4 is 0.75, so it's still getting larger. 4/5 is 0.8, 5 over 6 is 0.83 bar. So we'll see that the fractions keep getting larger and larger, but since the denominator is always bigger than the numerator, it will never pass the value of 1. And this sequence, if we look at it graphically, it's getting closer and closer to 1, and we say that the limit of this sequence is 1. Okay, look at one more example. Here we are looking at the sequence -1 to the n times n over n plus 1. So we just looked at this n over n plus 1 sequence, now we have the negative 1 to the n in front, which makes the values alternate. So instead of just having 1/2, 2/3, 3/4, we have negative 1/2 for the first term, negative 1 to the first power is negative. For the second term, negative 1 squared is positive. Third term, negative 1 cubed is negative, so the signs keep alternating. And in this case, even though the values keep getting, the absolute value of the values keeps getting close to 1, and the fact that it alternates does not let us get close to any one particular value. The positive numbers get close to positive 1, while the negative values are getting close to negative 1. And in this case, we do say that the limit does not exist. The sequence diverges. Right, so that we've defined what we mean by taking a limit of a sequence, we're going to look at some limit laws for sequences. So if I have two sequences, a sub n and b sub n, and they're both convergent sequences, and if we have a constant c, the following are true. So limit of a sub n plus b sub n, as n goes to infinity, is equal to the sum of the two limits. Limit of a sub n as n goes to infinity plus limit of b sub n as goes to infinity. So the limit of the sum is the sum of the two limits, and the same is true for the difference. Right? Next rule says if I have a limit of a constant multiplied by the terms of a sequence, that is equal to the constant multiplied by the limit of the sequence. Limit of a constant is a constant. So if I have a sequence that's made up of a constant term, so the sequence would, for example, look like 5, 5, 5, 5, 5, 5, 5. The limit of that sequence would be 5. If I have a limit of a product of two sequences that converge, that is equal to the product of the two limits. I can find the limits of the two sequences separately, multiply them, and the same is true for the division, as long as the limit of the denominator is not 0. Right, so otherwise we would have an undefined. Right, and if I have a sequence whose terms are taken to a power, and I want to find the limit of that as it goes to infinity, I can find the limit of the terms of the sequence and take the answer to the same power, as long as both the power and the terms are positive. Again, the result of that tells me that if I'm taking a limit as n goes to infinity of 1 over n to any power, again, as long as the power is positive, we are going to get 0, right? So 1 over n is a sequence that keeps getting smaller and smaller and smaller. So the limit as n goes to infinity of 1 over n would be 0. And then if I take that to the power, it is 0 to a power, which is still 0. Okay, we're going to apply that in our next example. We want to find the limit of that fraction, n plus 4n squared over 3 plus 5n plus 8n squared. And the limit is as n goes to infinity. Right, so what we're going to do in this case, we're going to take the numerator and the denominator and divide them by the largest power of n in the denominator. Right, so it's a standard thing to do when you have a fraction where you have a polynomial on the top and a bottom in a sequence. So we'll take the largest power in the denominator and divide that both on the top and the bottom. And since I'm dividing it both on the top and the bottom, the value of that fraction is stays the same. So we divide top and the bottom by n squared. That's the highest power of n that's in the denominator. And that break up these polynomials, put each term over n squared. And then I can simplify some of these fractions. So for example, 4n squared over n squared is just 4, and 5n over n squared I can reduce by power of by one of the n's and get 5 over n, and 8n squared over n squared is 8. Right, so now applying some of the rules we just saw, I can write this as a 5 times limit of 1 over n squared as n goes to infinity. Right, so that's the constant 5 can be taken in front, and then I can take the sum on the top and write it as the sum of two separate limits. So then I have a limit of 4 as n goes to infinity in the numerator. In the denominator, we have 3 times limit of 1 over n squared as n goes to infinity, plus 5 times limit of 1 over n as n goes to infinity, plus limit of 8 as n goes to infinity. And we just saw that some of these limits are just 0, right? So we said limit as n goes to infinity of 1 over n to any power, as long as the power is positive, is going to be 0. So I'm going to have 5 times 0 on the top. Limit of 4 is just 4 because it's a constant. On the bottom, we have 3 times 0 plus 5 times 0 plus limit of 8 is 8. So we have 0 plus 4 on the top, 0 plus 8 on the bottom. 4 over 8 reduces to be 1/2.